Okay, so once again, we're here for the 22nd Clarke Prize, and you all know this, and you hear me every year, but we give it out for excellence in research. And the idea is, and this goes back to Joan Irvine Smith and Athlete Richardson Clarke and Ron Linsky, which I know many of you knew. They really wanted to use this to raise awareness of the work that goes on out there by researchers in the area of water. And, you know, Joan Irvine Smith, and I've learned this from her son Jim as well as from herself, they were always very interested in water and water supply for their ranch, whether it was orchards or livestock. I mean, in Southern California, as many of you know, even if you're not from here, it's very engineered in terms of how water supply is provided. So that goes back to the ranches that were here, the city of Irvine Ranch Water District. There's a long history there. So we are here to award the 22nd annual Clarke Prize. I'm trying to think if there's anything else I wanted to say. There's two things that go along with the Clarke Prize, a medallion and an award of $50,000. So we were actually talking at our table, and that's a big deal. There's a lot of awards out there. The Clarke Prize is an actual prize, and we were talking about folks like the Lee Kuan Yew Prize in Singapore was actually modeled on what we do here, and it's actually very well known in the research community, and I think our job is try to make it more well known in the community at large, in the public awareness. So what I'd like to do is invite Joe Hughes to come up. Joe Hughes is going to introduce our 22nd recipient, the 2015 recipient of the Clarke Prize. I just want to give you a brief background on Joe Hughes. He's with Drexel University. He actually nominated this year's award. That's why we actually invited him to come out. He was very gracious to do that. He's the Dean of Engineering, and he's a University Distinguished Professor at Drexel, which is in Philadelphia, Pennsylvania, and he's the founding director of the A.J. Drexel Institute for Energy and Environment. Joe, can I have you come up and introduce this year's recipient?
It is a distinct pleasure to be here tonight to talk about John Crittenden. Nominating John for this award was one of the easiest letters I have ever written. It just flowed from the fingertips, and it was really a joy to write. And to hear that he received the award was even nicer. John, congratulations.
Joe, can you hit okay for me?
I have no idea what just happened. I'm technologically illiterate. Where's okay?
Okay, the next slide.
John, that's how you nominate somebody, is when you can't even use a computer, right? I'd like tonight to be a celebration. We're talking about an amazingly accomplished individual, someone who's done remarkable things, and we get a chance tonight to say thank you. And to me, that's a celebration. John? As everybody knows, I'm not a big PowerPoint man. It really is a privilege to have had the opportunity to honor or to nominate John for this award and to be here where he's being honored. I'm not going to read his CV to you. If you want to read his CV and find out what a really accomplished academic and engineer has accomplished in their life, in our field, look at John's. I'm not going to read it to you, but I encourage you all to take a glance at it. There are a few things I want to tell you about John, but I'm going to start with a story, and Sheen, this is for you. Okay? I met John in 1990 on the Michigan State campus in East Lansing. And I was a graduate student. I probably still should be. And I was standing next to my advisor, Gene Parkin, who I think the world of. And John walked in the room, and he had a leather jacket on. It was kind of like a bomber jacket. You know, it was not very academic, let me just say that. And it was a reception, and so people were having a bottle of beer or a glass of wine. And John had a bottle of beer in his hand, and he was drinking it out of the side of his mouth. I was a graduate student. I remember this like it was yesterday. And I'm getting pretty old, so remembering is not that strong with me, okay? And my advisor leaned over to me and said, "That's John Crittenden. He's cool." That's how I met John. Honest to God. So you can keep that story as long as you'd like. Your husband is cool. There's three things I want to share about John that people probably know, but they need to be said. John, first, I can only describe John's drive and work ethic with only one term: absolutely relentless. I have never met anybody who wouldn't shut it down, who always had to do more, who always had to work on issues that were spinning in his head like John. I've had the opportunity to work around an awful lot of academics, an awful lot of really bright people in the consulting sector, the government sector, et cetera, and I have never seen it like that. Absolutely relentless. And John, I don't know how you do it, but don't stop. The second thing that many of you may not know is how students respond to John. It's really an interesting, balance. On one hand, there's incredible respect. And on the other hand, there's complete and total fear. Because they know, and I've been in the room too many times when John is interrogating a student. No, I know, this is going to all end positive, John. But the student walks into the room and they know that Crittenden's there, okay? And they know that it's going to be tough. It's going to be fair, but it's going to be tough. And I've seen this at all levels. I've seen it even with high school students, and I've seen it with PhD students. So let me give you one specific example. And John, the point here is the positive effect that you make on people's lives. We had a student, his advisor was Jae Hong Kim. And for those of you who know Jae Hong, he is a really rigorous scholar. And Jae Hong is never going to put somebody in a room who's not going to pass the exam. And I read the thesis, and I might have found a grammatical error. But in terms of theory and application, it was absolutely perfect. Perfect. And it was a no-brainer. You're going to go in, 20-minute presentation, talk for a little while, shake their hand, call him doctor, and let him go, right? He gave his presentation, and John engaged. And John engaged in a discussion that was deep, meaningful, mathematical, quantitative, and difficult. And the student and John were like watching dueling banjos. And John just kept picking up the pace. Okay? And the student responded. And the student did very, very well in light of the pressure of the situation. And then at the end, John shook his hand and said, "Best dissertation I ever read." And that kid grew about 4 inches. And if you don't see it firsthand, you don't understand it. But John makes his students and other students achieve and understand what it means to excel. I don't know if you remember that, John. I can't forget it. I was blown away. The third thing I want to say about John, this is really a chronology of his career. If you look at what John's worked on, he has seen what others don't see, but in retrospect, everybody understands it's important. And I'd start with green chemistry, John. I think the work that you did in Michigan Tech was enlightening to a huge community that now is actually a profession. And I think what you've done in sustainability, much the same, much more recently. I think you've seen problems, challenges, opportunities, whatever the right words are, before other people do. And then a few years later, excuse me, I'm supposed to be able to talk for a living. A few years later, people are like, yeah, of course, that's the most important thing. But John's 3 years ahead of him. And I think that is a really amazing quality and trait, and it's very rare. Well done. So I'm in Beijing a few weeks ago with John, and we're at the Global Grand Challenge Summit, and we're sitting next to each other. And the person sitting right in front of us is will.i.am. No, it's true. Black Eyed Peas, lead singer, right? And I'm looking at the guy sitting next to will.i.am, and I said, I feel bad for you, because I'm sitting next to the rock star. I was sitting next to John. He did get his picture with will.i.am, though. I'd like to wrap up. I've taken too long. I'd like to, and I may be overextending, but I'd like to thank, from the perspective of our profession, I'd like to thank what John has done. And on a very personal level, thank you. You've done a lot to help me grow, to help me learn, to push me, to challenge me, and that's rare too. So thank you, John. So I would like to thank the committee that saw the wisdom in the nomination of John Crittenden for this award. I believe it's well-deserved, I believe it's timely, and I believe it's time for you to get on stage and for me to sit down.
So yes, John, come on up to the stage. I also like to invite James Irvine Swindon of the foundation and Morton Irvine Smith to come up with the presentation.
Before we award our recipient this evening, I thought it was appropriate that we also thank Jeff Mosier of the National Water Re-Institute for everything that he does to make this happen, and also to carry on the incredible vision that our mother and our grandmother had. And more to the point, I want to thank everybody in this room, because you are the ones that are in the trenches, you're the ones that are actually going to put forth and be able to preserve that incredible liquid we have on the table, without which life doesn't exist. And so I think all of you deserve an incredible hand for the work that you do and that you will continue to do in order to preserve our resources and our planet. Thank you. But tonight, it is my great honor to present the 2000, I'm getting back to when I first came to these things. The 2015 recipient of the Joan Irvine Smith and Ashley R. Clarke Award to John Crittenden. Congratulations.
Thank you.
To quote my mother, this is my favorite part. I'd like to award the $50,000 prize that goes with the Clarke Prize, and John will be buying drinks after dinner.
So we know there's no such thing as a free dinner. And along with the Clarke Prize, we always ask our recipient to provide a talk or a lecture. And John, I'd like to invite you to come up to give your lecture for this year. Thank you.
Okay,
And
thank you.
congratulations.
Thank you, Jim. Well, that's a little overwhelming. Okay, well, I'll try to live up to such kind words that Joe gave. And I really appreciate everyone's support. A lot of people in this room have had a huge impact on my life and my career. Just to name a few: George Chabanaglos and Rhodes Trussell and Dick Luthi and Jan, of course, and my wife. Jan is my sister. And Perry, so they've had a lot of, and many. I could just go on all night, but so many people have had a really huge influence on me and helped me shape my career. Well, today, I hope I can not take too long with this. I prepared this talk, and if you look at the written document, I have a lot more details in there, so I've left out some, fortunately, so that we wouldn't be here all night. So the title of my talk is Water for Everything and the Transformative Technologies to Improve Water Sustainability. What it is a play on words, you know, like Stephen Hawking, the theory of everything. Well, now that the cosmos has been created, we need water for everything that in the place we live. So I'm going to talk about where we use water, how we use it, and what technologies we might be thinking about in the future that will improve its sustainability. Well, a couple of opening statements here. First of all, I got to say that we need to recreate the anthroposphere. This is my little definition of sustainability. To exist within the means of nature, that has two important criteria. We have to use renewable resources in the long run, and we have to not interfere with natural cycles in such a way that we destroy them. And I'm going to talk a few words about that in a moment. This is going to be a greater challenge than we've had in the past, because now we're going to have to examine interactions between the natural, engineered, social, and economic systems. So that's a little more expansive than what engineers have typically dealt with. And also, I want to say there are two major things that we have to focus on if we're going to improve sustainability. And one is systems level thinking. There will always be room for reductionist engineering, for sure. But I think the greatest gains for sustainability will be met with looking at systems, and I think I'll try to prove that tonight. And then the other piece is managing complexity, and you're right now trying to wonder, what do I mean by that? Well, I'll make that pretty clear in a little while. So those two things, systems level thinking and managing complexity. Well, there's a thing that a thought piece we came up with a number of years ago we called the Gigaton problem, and I want to explain what I mean by that. Basically, if you look at the far left there, we can start from the far left and work to the right, the bar graph. Right now, we are 7.3 billion people on this earth. We use about 78 billion, or gigatons, of material in the world economy, and only 28% is renewable. So we're failing on that one criteria I mentioned. We need to use renewable resources. Right now, we use 13 8.3 billion tons of oil equivalent of energy, and only 18% of that is renewable, so we're also failing in the energy sector as well. When it comes to natural cycles, the next one pertains to that, and that is that we release 8.6 billion tons of CO2 from burning of fossil fuels. And so we have dramatically interfered with the carbon cycle, and this, as a result, we're finding the planet to be warmer. So the other criteria about interfering with natural cycles, we're failing miserably as well. We use about 3,900 billion cubic meters of water. That's about 43% of the available fresh water on the earth. Obviously not sustainable in the long run if we continue to use more and more water. And then we have about 1 billion passenger cars. So I call this whole thing put together the Gigaton problem. And for those of you who want to understand what I'm trying to say here is that if you're doing work and you're working on some technology, I'd like to say that if you're working on sustainable engineering approach, when you bring your technology to scale, will it solve a gigaton problem? One more thing I got to say is that the golden billion that live like we do on this earth created this gigaton problem. And if you want to think about what's happening in 2050, you might want to multiply it by 10. Especially if you want to think about it from the point of view of being egalitarian. We want to have everyone have the equal opportunity to live as we do. So if we want peace and safety of the world, that's something we have to consider. Okay. And of course, I put up here on the right where we use water. We use water in almost all of these activities. And I'll give you some more examples here in a moment. Well, climate change. Oh, what happened? I think what happened is you copied my slides into here and then you didn't keep the original. Oh, well. Anyway, climate change. So, you guys go with it, I know. Well, I'm not going to say much more about climate change. I think we've talked a lot today already. We know it's getting warmer, and this has been indicated here on my graph. And then we also see severe droughts, and that was discussed all day long, so no reason for me to continue that discussion. But, you know, here in the West, we have more droughts, and the Palmer Index is quite high for extreme droughts, for example. And then we also have El Nino out there. So what portends of what might happen in the future? In the high desert was earlier this month, they had a fairly significant rainstorm. They had 20-foot wall highs of mud flowing. So now California is going to be having an interesting problem. They're not only going to have to deal with droughts, but also floods at the same time. So that's going to be an extra challenge for everybody. Well, here's another thing that you may have seen in the news. It was April 16th, 2014, Farmers Insurance Company filed a lawsuit against 9 municipalities in and around Chicago. They said, guess what, folks? You municipalities failed to prepare for climate change. And farmers, of course, had to pay a lot of money for storm sewers or storm waters that had overwhelmed the sewer systems and flooded homes and businesses. And they said that municipalities failed to take action to prevent such a problem because everyone knows that climate change is out there and that they should have prepared for it. Well, they eventually dropped the suit, but this is just a bellwether of future. In the future, for those of you in municipalities, you may have to prepare for such events. Okay, so now what I want to do is give a little bit of a system view of water. And first of all, we're all pretty familiar with water is used for energy. It's a little hard for me to see this. Okay. Whoops. So here you can see the amount of water that's required for a million BTUs. And you can see at the top of the list in terms of amount of water, corn ethanol is, sorry Jerry, we need an awful lot of water for producing corn ethanol, and I know that Iowa's big into that, so. So anyway, you can see the list here, and you can look at those numbers in the report, but, you know, at the lower end, perhaps we can see natural gas and transport is on the lower end, so. The other thing is, we need water for energy and energy for water. This is pretty much old hat. We all know about the water energy crisis, or nexus, I should say. And on the left there, you can see that hydro is probably one of the highest in terms of evaporative loss, gallons per kilowatt hour, because you have an impoundment right, and the water evaporates from the top. You still make power, but it requires a fair amount of water. And at the lower end, you can see the renewables needing a little bit of water, because of the fact that you need water to produce those technologies. And on the right, you can see the other way around, the kilowatt hours per million gallons for treating and distributing various kinds of surface waters or groundwaters and so on. Well, I won't belabor that, but that's pretty well known. What I'd like to do now is say something about ag. Ag is a really huge user of water. And really, I'd like to say that livestock in this current form is really unsustainable. Do you know that 30% of the ice-free earth is used to raise feed for livestock? And again, that's the only golden billion are probably having that benefit of eating meat. And as you see on the far left there, chicken, 1 kilogram of chicken requires 5.5 pounds of feed, 1,000 gallons of water. And then if you look at pigs, it's 11 pounds of feed and 1,500 gallons of water. And then on the far right there, cattle requires 22 pounds of feed and 4,400 gallons of water. So, you know, that 16-ounce steak, there's actually 2,000 gallons of water embedded in that. So this is really, I don't think it's, in the long term, a sustainable activity. And I'm going to say a little bit more about other ways that you might be able to have something like beef. So I forget who I was talking to about the water consumption in California. Thought I'd give some California numbers here. On the far left there is alfalfa. You can see how much water is used for that. Who knows why you grow such a low value crop, but anyway. And then next is rice. Well, I mean, you know, feed to the cows for milk, but all right. Rice, we got lots of rice out there, pasture land, but then we have the almonds and pistachios and corn and so on. You can see the numbers as they go down. So it turns out that agricultural water consumption and use in California is about 8.7 million acre feet. And you can see there's another little line that goes up and down, and over onto the right is water efficiency. And you can see that there could be some improvements there. It's barely readable on this. Maybe it's more readable on the slides there, but ranges anywhere between 0.6 and 0.8. So we might have some opportunity there for additional water conservation there. Here's some fun facts about the California agricultural economy. First of all, I guess everyone knows that California is the country's largest agricultural producer and exporter. Did you know that? Yeah. How about the fact that you produce more than 400 commodities, primarily comprised of specialty crops, almonds, grapes, and strawberries? That's what I meant about that comment about alfalfa. Grow more of that. And the agricultural production was valued at about $47 billion in 2013, about 17% of the U.S. total agricultural output. Now I'm returning to the part about unsustainable livestock. It turns out that maybe we could make more sustainable meat and dairy products from plants. First of all, we should understand that there's 400,000 species of plants, and each plant has more than tens of thousands of proteins. And so there might be an opportunity there for making food that mimics the texture and taste of animal-derived food from plants. And obviously there'd be huge efficiencies in terms of energy, water, and other inputs. So they could be cheaper, healthier, as satisfying as animal products and much lower environmental impact. And there's a number of tech startups here again in California, only they have the hubris to take on, you know, the agricultural industry in the United States, but are trying to develop some of these. And here's some examples. Smart strips, I don't know if you've seen these, called Beyond Meat. They're pretty good. You can buy them at Whole Foods, or sometimes we call it Whole Paycheck, but, you know. Anyway, eggless mayonnaise. And then there's these plant beef burger patties made by Impossible Foods. I was told that, or I read that perhaps the first versions were not that good. They kind of tasted like rancid polenta. So they missed the mark there. And one of the other tech startups, the fellow who's the CEO, they developed this beverage called Soylent, made out of soy and lentils. And maybe you're thinking of Soylent Green. There's actually human flesh. But anyway, this is soybeans and lentils. So the CEO, what he did is he converted his kitchen to a library, and he had no cooking utensils because he wasn't going to cook. And once in a while he goes out for what he calls recreational eating at the restaurants. So, okay. But that Soylent drink, 3 times a day, you drink it up, all the nutrition you need. Okay. Yeah. Well, one threat might be vertical farms. I'm going to show you a little clip on vertical farms here in a minute. But also indoor farms or greenhouses. And this is a comparison between a company that started in Georgia where they're going to grow hydroponically romaine lettuce. And of course it's closer to Atlanta, and so there's fewer miles that you have to travel. But the land requirements are interestingly different. Almost a square mile, 620 acres is required for these 33 million heads of romaine lettuce. And it only require 20 heads of lettuce, 20 acres of lettuce. The other numbers we'll kind of skip over them, but the carbon footprint's about a quarter. You don't have to travel, 2,500 miles from California to bring it to Atlanta. And then the water use drops off dramatically, roughly 64 million gallons compared to 0.3 to 1.5 billion gallons of water for field grown. I have to add a caveat here. These folks, they haven't built the farm at this scale yet, but it looks like there might be some efficiencies here, and I'm going to show you how we might integrate this into an urban system and design in a moment. So my YouTube video, I want to show you a little. This is a vertical farm that was produced in Chicago, and it's kind of neat. The video looks better than this slide here.
This is today's Green Minute, and I'm Jim Parks. This former meat processing plant in Chicago is about to become a unique food-producing facility called The Plant. And the brilliant part of its design is that the foods it will produce are selected so that the waste from one becomes the raw material for another. Watch this. The plan is to bring in a kombucha tea brewery, a hydroponic vegetable farm, a tilapia fish farm, a brewery, a commercial kitchen, and at the heart of the system, an anaerobic digester that turns organic material into biogas, which is piped to a turbine generator to make electricity for plant grow lights. The plants make oxygen for the kombucha, and the kombucha makes CO2 for the plants. Waste from the fish feeds the plants, and the plants clean the water for the fish. More fish waste goes to the digester, along with plant waste, waste from outside sources, and spent grain from the brewery. Spent barley from the brewery feeds the fish. Sludge from the digester becomes algae and duckweed that also feed the fish. Now, along with electricity, the turbine makes steam, which is piped to the commercial kitchen, the brewery, and the entire building for heating and cooling. So, we get kombucha tea, fresh vegetables, tilapia, beer, and food from the kitchen, all with no waste. Add to this that the plant will add 125 green jobs in a distressed area, and that's state-of-the-art integrated food production.
So I'm going to talk about integrating urban farms and some of our ideas here in a moment. So we also need water for materials. Here you can see on the far left there, this is cubic meters per ton of steel, about 3, and it ranges across here to, well, gold is one of the highest, nickel, copper, and so on. So it's not so interesting to study these numbers and so on, but I just want to make the point that water is required for production of these materials. One interesting thing you may not know, that in 2013, gold production in California was 146,000 ounces, and that required about 848 acre feet, so interesting. Another way to look at water is to look at its productivity for various industries. And what I have plotted here is the amount of water required per dollar. So the dollars per, dollars that are generated, per gallon of water. On the top, you can see the ag is really on the low side. You need a lot of water to produce $1 over there. Whereas in the middle there, finance and insurance, they don't use much water. And so then the productivity is much higher. But again, water for everything, okay? All right. We also need water for transportation. And this is looking at the impact of fuel types and vehicle technologies. The benchmark there is sort of fourth one over, unleaded gasoline at about 0.32 gallons of water per vehicle mile traveled. And then if we go back to picking on Iowa for a moment, on the corn ethanol, you can see that we need about 4 gallons of water per vehicle mile traveled. And switchgrass, if it's irrigated, could be quite high, 12 gallons per vehicle mile traveled, and so on. One thing that we've heard an awful lot about is electrification of transportation. And we did a calculation for the city of Atlanta that if you electrified all the vehicles in Atlanta, that you would need about 91 million gallons of water, that's evaporative loss, to power those vehicles using the existing power generation system, which basically, you have a thermoelectric power plant, rejects heat by evaporating water. It's almost the same as a domestic consumption, and that would definitely not be a sustainable approach. So we got to have more renewables and some technologies that don't use as much water if we're going to electrify transportation. Okay, so now I'm going to get into a little bit about 4 different technologies and their integration, including some of the ones I've just talked about. So first, it's interesting, of course, to look at the water resource profile in the United States, and you can see there the 3 big ones are thermoelectric power generation, the next is irrigation, and the next one in line is public water supply. And what I'm going to talk about are some technologies where we can help reduce that amount of water. One is the decentralized energy production. Urban farming, I've already mentioned a little bit. And then we're never going to replace, wheat and corn that way, but certainly for the high value crops, we could probably reduce the amount of water. And then the last is decentralized water production. Okay, so earlier today there was quite a bit of discussion about what we call low-impact development. Basically, what we've done in the past is we've taken and scraped off the ecology and covered it with hardscape, and now we got a stormwater problem. And so instead of that land being a sponge for water, it's a place for water to run off and contaminate surface waters and the like, and cause erosion and so on. And so what we mean by low-impact development, there's some examples here on the upper left, is rain gardens for flood control, green roofs over there. Down below, a more attractive looking rainwater harvesting tank. In the middle there is a green alleyway that's produced by, this is for Vancouver. What they did is they took, they used wetlands to treat the storm water and then let that flow to the salmon-bearing rivers, and there was green alleyways that can have lots of benefits, like mitigating heat island, as well as providing places where you might bike safely, recreational opportunities, so on and so on. And then porous lots. So that's some examples of what I mean by LID. Well, these flows only make sense in Atlanta, so I'm not going to spend too much time on it. And we heard a little bit about this earlier today, but the potential for rainwater harvesting at the top here in Atlanta is quite large. And if we use that for non-potable use, these are some of the numbers that you could come up with. But downstream, you're going to have a wastewater treatment plant that's still as large as it would have been if you'd gotten all of your water from a centralized plant. This sort of recognizes that you can't get all the water you need from rainwater harvesting, that you're going to have a centralized connection anyway. But then if down below we have the gray water system where we're reusing the gray water. I won't get into that in too much detail. But basically, it's potentially, if you use rainwater harvesting with that, what you could find out is you could be off-grid for the water supply piece. And then downstream, you're going to have a much smaller wastewater treatment plant. So that'll have some benefits that we'll talk about later. But in particular, it'll be more highly concentrated and be better for nutrient recovery and energy recovery. Okay, so now my systems idea, and we still have to implement some of these and see whether or not they work well. But here's sort of the overall view. So on the left here, what we have is, we've employed rainwater harvesting, and we don't have as high of a flow in the sewers. And then downstream for that, we have higher concentrations, which will facilitate the getting the nutrients and the energy from that. And then in turn, that can be used for our urban farms. The nutrients can be used for our urban farms. Some of the energy that comes from that could be employed for our energy infrastructure. For example, if you create these green alleyways and so on, you could mitigate heat island effects, reduce the amount of energy that's needed. Also, if you use the nutrients and water for creating this green space, what you're going to find is that this could have an impact on cycling and pedestrians and so on. So this sort of integrating this into the system may have some benefits. And I have a couple other ideas as we move forward. Earlier, George was talking about the water was being too hot. Well, that's perfect. Let's harvest that heat. And this is an example of the False Creek neighborhood energy utility, which basically mines the heat from the sewer. And this is the Olympic Village here that was in Vancouver. You remember the Winter Olympics there in Vancouver. And they can recover 70% of the annual energy demand and reduce greenhouse gas emissions by 50%. So there's energy in the water as well. Another technology, so I'm going to tell you the 4 technologies. One is this LID and fully implementing it. The second one is looking at decentralized energy production. And so let's build the case. So on the far left there, what we have is what's called an absorption chiller, and you can send heat into there and get cooling out of it. And then the second device here is a microturbine. These are all established technologies, but we're going to try and combine them in a unique way. Anyway, so these turbines produce heat, which can be used for heating or hot water, and then that heat, again, could be used for cooling as well. And then they also produce electricity, and so if you follow the heating and cooling load of this building, this is the Perkins and Will building, it's about a 20,000 square foot office building, you can supply about 40% of the electricity that the building needs if you match the thermal and heating load. So that's what I mean by this combined cooling, heat, and power. And if we try to expand that, 2.0, I guess, here's your conventional system on the top. You're heating this is your building. You heat it with boiler or with natural gas furnace. And you get electricity from the grid, and that for both plug load and also for cooling. That's the conventional. But down below, we start to add more and more components. So we still have our combined heating, cooling microturbine, which will provide some electrical energy. It'll provide heat as well. And then if we can add to that heat storage, our absorption chiller, and then add other pieces like storage in cars or flow batteries or what have you. And then we can add in renewables as well. And the benefits of this is that with this microgrid now, renewables have some problems once in a while when they have a fair amount of variability. The sun goes down or we get a wind drought or whatever. We need to have some spinning reserve that we can bring up to speed fairly quickly. Well, this microgrid has it all. It's got storage of heat, energy, ability to create energy from natural gas, as well as renewables. Put that mix together. Okay, so what we might be able to do then, if we start looking at combining some of these things, This one right here, if you'll notice on the bottom, we've got a number of grids here. We have the natural gas grid, which is purple, heating and energy is yellow, water is blue, black is fertilizer, and then the last one there is for CO2. So here's the idea. We, in the upper left, we still have our storm management and low impact development. We get more concentrated wastewater. We can get on-site nutrient energy recovery. This can have an impact on our urban agriculture. The nutrients, let's see here. Yeah, the natural gas can be used for combined carbon capture, cooling, heating, and power. So now what we have is our microturbine that gives off a richer CO2 level. We can use that in our urban farm. Or maybe we have facades on the building that's growing algae. There's another way of capturing some of that CO2. And then we have heating for the composting, heating for the agriculture. And so the idea here is to start closing these loops, because that's what we have to do in the long term. You know, close the carbon loop, close the nutrient loop, close the water loop. So it's a tiny step towards that direction. Okay. Now, you might wonder, why would I talk about transit-oriented design and autonomous vehicles? What in the world does that have to do with water? Okay, I'm going to tell you. First of all, if you have a city that's spread out like this one, there's going to be more miles traveled. And I think I showed you how much water is required to create transportation fuels, right? Okay, so the idea with transit-oriented development is to build high-quality transit centers that are supported by the right density. And so, you know, we have affordable homes, walkable communities, mixed land use, and multiple modes of transport. You know, walking, bicycling, and of course the high speed, or the not necessarily high speed, but public transportation. Now, we can also throw another technology on the mix here, and that's where we look at autonomous vehicles. And you say, well, what would autonomous vehicles have to do with this? Well, we estimated that if you had 80% penetration by autonomous vehicles, we would have 28% less cars on the road. And by the way, all those lanes you have on those freeways, and we might have plenty of room, by the way. 72% reduction in parking space, 24% reduction in impervious area. And look at this, an additional 17% of the city land that could be used for green space and stormwater management. Huge. Okay, so now what happens if I put all this together? Low impact development, gray water reclamation, rainwater harvesting, air-cooled microturbines, residential PV and wind, thermal and electrical storage, vehicle-to-grid, urban farms, transit-oriented development, autonomous vehicles. What we found in our management of complexity is when you start putting some of these things together, the adoption rate goes higher. So that's why I'll say something about that. And I can't read that at all. Yeah, so when you copy these slides and you didn't copy it, well, I keep my settings. Anyway, so it's blank. Anyway, the idea is by putting these together, we get more preferred communities and desirable communities. And on the far right, all the good parts showed up. The possible cumulative effects, which something we'll have to look at in detail to play this all out. But reduce water and energy consumption, lower dependence on centralized systems, larger share of renewables in the energy mix, reduce vehicle miles traveled, even an increase in property tax. I don't have time to explain how that works, but it's true, and enhance system resilience. Okay, I'm going to skip that. The last little piece, this is sort of systems thinking, the last little piece I want to talk about is what I call managing complexity. And what I want to just show is a graph here. So what happens is that on the micro scale, we have where we live, where we work, where we go shopping. They interact in this socio-economic infrastructure system, and properties emerge. And in the past, we did all of our work down here as engineers, and we didn't think a lot about what's going on up here. So on the left is a land use map for Atlanta, for example. And the quality of life could be, you know, air quality, traffic congestion, that kind of thing, water footprint, energy footprint, and so on. So these properties emerged. Now, I don't think you really wanted to design bad air, did you? No. You just built a transportation and electrical power generation system that gave you bad air. So what I mean by managing complexity is giving looking at the emergent properties and trying to work with your stakeholders and make sure you understand what they really want, give it to them that it's more sustainable. When you put those things together, those attributes together, you can find better adoption. This is what we really want over here. So, so one of the things that we've been looking at was big data analysis for social decision-making and complexity modeling. You know, we look at a variety of data, social media, blogs, Twitter, news, lots of other things. And from that, we can analyze that information to try and see what are people talking about, so the topics that they're talking about. What is the sentiment? What are they in favor or not in favor, that type of thing. And then from that, we can build these models to predict the demand for this new urban infrastructure, and that's the idea. And what we're finding is that when you put more of the attributes together, we get greater adoption. And I won't bore you too much with that, but I'll just stop with that point right there. Oh my, this is really, okay. Those two are bad. I wish I could have showed you, I don't know why it's doing this. No, I don't know. Yeah, there we go. Well, we have the Smart Track data, which has information on 1.3 million parcels in Atlanta. And the kind of information that we have is, if you look at a smaller scale, is shown there, like 30 different attributes, so we actually know what's going on here. If I plug in the climate file, I can calculate the energy demand of 1.3 million buildings. And so that's going to roll back into how much energy is required. It's going to roll back into how much water I'm going to need, and so on and so forth. So what I did is to take that information, and then we looked at two scenarios, and I'm not going to say anything more about this business as usual, but this is this more sustainable development, which requires less sprawling or has less sprawling. And if you look carefully, you'll notice that the yellow, which is the medium residential, low density, medium residential density buildings, you can see that it's about the same as it was in 2005, whereas the business as usual, we spread out more and more. Anyway, what we did then is to fully implement decentralized combined heat and power, and how would it work out? So on the far left there, you can see that the water withdrawal would drop 57%. And then on the right, this is the evaporation or evaporative loss. You'll see that we get a 52% reduction in that by using this technology, because remember, the air-cooled microturbines does not need any water, so it breaks the water energy nexus. And the interesting thing here is that you can see that, yes, we should think about the public water supply, and that's important, but if you really want to save water, in this case, you can reduce that amount of water by 2.5 times the amount used for domestic consumption by implementing some of these other technologies. And the other benefits are shown here. We get a 23% reduction in CO2, a 65% reduction in NOx, and that's important because NOx does two things. At the ground level, combined with VOCs and light, we get ozone. The other thing is that they can accrete into PM 2.5. And the energy costs look less, but I always have this theory about whenever you do an energy or cost estimate, there's the pi rule. You know what the pi rule is? You take your cost estimate and multiply by pi. That's probably more realistic. But anyway, all right, so it looks like the life cycle costing looks favorable. But you're not going to walk away from $3 trillion worth of investment in the existing power generation, not in one swoop. So we have to keep that in mind. So anyway, we're finally right there. How long did I take? Oh. Anyway, infrastructure systems are all connected, and maybe greater sustainability gains in water management can be achieved by looking at all their interactions. Decentralized water, low-impact development can save water, energy, and money. Decentralized energy and combined heat and power may be able to save energy, water, and money. Transportation and land use is very important. And maybe we can use some of these complexity models to help us for the decision making. The last little thing there, I put a caveat on here. To really see if this works, there's 3 steps. First, we do some calculations on the computer to see if it's going to save any money, if there's any benefits. Then the second thing, you build it, and the third thing is you evaluate whether it performs the way you expect it to. So we're not anywhere near that third step. We're back on the first step, still building what's going on in the computer, looking at whether or not it looks reasonable. So these are some of the emerging engineering solutions for water and human sustainability, and they're listed here. Energy independent buildings, living buildings, high performance buildings, in the lower right there, decentralized energy infrastructure, grid scale energy storage, flow batteries, supercapacitors, solar powered transport. And we have one we just built in Atlanta for solar power transport, sort of a demonstration. Efficient water use, decentralized water infrastructure, and then transit-oriented design, bike-friendly neighborhoods, et cetera, all coming together. So those are some technologies, when we start thinking of how they might work as a collection, would be, might have some benefits. So with that, I think we finally have the last of this. And anyway, thank you so much for your attention. And I don't know if we have time for questions or not, but okay.
Sure, John, if you're willing to take questions from this crowd, we'll go ahead and...
Well, first of all, you know that mayors are the most popular politicians, right? More popular than any other politician for some reason, because they do things and they get things done. That's, yeah. So, but anyway, on the other answer, what I can say is that I didn't show it about complexity, but it turns out that on social benefits, as you increase the number of people in a city, we see higher increases in GDP, wealth per person. So all of that seems to scale with larger cities on the social issues. But on the other piece, the infrastructure needs, roadway, surface area, cables, all of that seems to be less. So as we see larger and larger cities, that seems to be a lower number. So there does seem to be some scaling issues that are beneficial for larger cities. And on one side, increasing well-being and so on is positive, and then on the also on the positive side, using there's less gas stations, less all of that stuff. So that looks like it might have some benefits. So is there a limit? Well, okay, so I guess so. I mean, it depends on how many people want to live in the city and what that city is all about, and what can they provide in terms of their value to the world. So I don't know if there's any real limit to the size, but you know, trying to combine some of the technologies I mentioned before with maybe urban farming and recovering the nutrients, looking at some of these cycles. I didn't get into it, but you afforded me an opportunity to say something about the natural gas. So maybe as we move to the future and we have these energy grids that use natural gas, we might be able to close the loop on the carbon, because now instead of, as we start initially, we will be using frack gas and we'll be using fossil fuel gas, but in the long term, maybe biogas can be fed into the system. And why do I mention gas? It seems that the gas network or gas grid is going to be eminently simpler than, you know, the wires and the transformers and all of that with electricity. So, plus you get the added advantage of producing electricity near where you need it, so you don't have as much grid loss. So I think to the extent that it makes sense for clusters of individuals to get together to create more wealth, like Silicon Valley or others like that, okay, so maybe it does make sense to have a city of a certain size, but tough question, I think.
Well, very good, John. Thank you very much.
Thank you.
Congratulations. So, John, thank you for that, and congratulations. And as John mentioned, there is a lecture, a written lecture that he prepared. It's going to be posted on our website. We send it out through our newsletter. If you are not on the newsletter, you can feel free to leave your email with Brandy or Jamie up front, and we'll be sure you get it. But John, thank you very much. It was good to have you here. I also want to thank Jim Swindon and Morton Irvine Smith for attending. It's always good to see you guys. I want to acknowledge the Joan Irvine Smith and Athlete Richardson Clarke Foundation for your continued support over the years. Thank you very much. And Joe Hughes, thank you for your introduction. It was good to meet you at this event. I'm glad you were here. The previous Clarke Prize recipients, as always, it's good to see you. The audience, everybody for attending. It's great to have you here. And I'd like to thank Jamie and Brandy and Suzanne, the rest of NWI staff for their support. And we also have a lot of students here that we always try to get. So thank you very much for coming and have a good night.